Hello everyone. So today we will be seeing how a capacitor will respond to an AC source. So this is a capacitor C with capacitance of C connected to this AC supply, and we need to find the expression for current. So if I say at a particular time if the charge is Q, accumulated charge on the capacitor is Q, then C, if it is the capacitance, then voltage across the capacitance is given by Q upon C. So I want to find the expression for current. So you know the current, by the definition of current, you know this rate of change of charge with respect to time is nothing but current. So this is an expression, and if I use in this equation, if I put the voltage as this, because anyway the voltage we are giving is this only. So Vm sine omega t is equal to Q by C. So that is the thing we are having. So now if I differentiate this equation, obviously Vm is constant, omega will be outside, it is also constant, and the differentiation of sine omega t is nothing but cos omega t. And obviously dq by dt, 1 by c is constant, it will come outside, and dq by dt, if I say it is I upon c. So, no? So I am explaining it here. This q by c differentiate, if it is dq by dt, this 1 by c will be outside. If I differentiating with respect to time. So this will be this 1 by c will be outside, and dq by dt I can write the expression for as current. So anyway, you can write I is equal to Pm omega c cos of omega t. So by this expression, you can understand that if I talk in case of resistor, there you for a voltage supply of V equal to Vm sine omega t, you get current as Vm by R sine omega t. So from this expression, you can understand that here resistance is this. Similar to a inductive circuit in L case, we saw I as Vm upon XL sine of omega t minus pi by 2, because the current was lagging. Anyway, the one focus point is this. So to make the analogous study of this capacitor circuit to that of R and L, I can write this omega c like this: Vm 1 upon omega c cos of omega t. Anyway, this omega c I can write 1 upon omega c. These both are same thing. Moreover, if I write it in the more expression of a sine, this cos omega t cos theta can be written as sine theta if you shift that by 90 degree. So it is sine theta plus 90 degree. This you can know from mathematics. So obviously 90 degree shifted version of these are complementary functions, cosine and sine. So 90 degree shifting of one function will obviously give you the function value of the another function. So here you can write Vm. This is 1 upon omega c. I can write it as, I told you, xc. This is nothing but, just like in case of inductive circuit, we called it as inductive reactance. We are going to call it as capacitive reactance in this circuit. Capacitive reactance, and it is given by 1 upon omega c. So I can write in place of 1 upon omega c as xc. Obviously, from this identity, I can write cos as sine omega t. 90 degree in radians, I can write pi by 2. So if you compare this expression with the voltage expression supply, the current seems to be leading by 90 degree. So if I tell you this as the first equation, and if I call this as the second equation, you can refer these two equations. So you can write that from 1 and 2 equations, we see that in a capacitive circuit, capacitive circuit, the current leads. In that case, the current was lagging with respect to voltage, but here it is plus pi by 2, the current is advanced with respect to the voltage, so the current leads by the voltage by an angle 90 degrees or pi by 2 radians. So this is pretty clear from this expression. Moreover, if you see the phasor diagrams, you can also visualize the concept here, which way we have derived. So obviously from you can see phasor diagram as well. If I draw phasor diagram, okay. So if this I am taking again, I took voltage like this. Let me extend this graph so that I can. So if I say this is nothing but, if it is V, it is the curve for V, phasor for V, and if it is an angle of omega t, anticlockwise always in phasor diagram, it's rotating at an angle frequency of omega, these phasors. So according to the expression as I have, we have got current as nothing but Vm by xc sine of omega t plus pi by 2. One more thing, you can write this Vm by omega c. If Vm by omega c you took as maximum Im, you can replace this by Im. Okay, Vm by xc will replace by M. Anyway, if you plot the current phasor here, from this you can see it is more 90 degree more with along with this omega t. So if I see this, obviously current will be somewhere like this, and this angle is 90 degree, and this is omega t plus 90. Okay, so this is current. So this expression you have got for the this is the phasor diagram relation. Moreover, you can find the values by, if you current value of I and V, instantaneous value you can find when you see the projection on this axis, which is V sine omega t, and here V sine omega t plus pi by 2. Okay, anyway, this is the phasor diagram. So you can see this relation easily. Now let us see the case of power here. What is happening to the power? So power expression generally is V into I. So if I write the instantaneous power, it will be an expression for instantaneous power. So it is V sine omega t. You got it as, obviously Vm by xc I am taking as Im sine of omega t plus pi by 2. This is the expression we got. Obviously you can collect Vm, Im terms together, and you can write like this. Now again in this you can see an identity like the previous case. You can write this as, obviously I will use this identity, you know that, 2 sine A, and obviously this you can write it as, from earlierly you wrote it as cos of omega t. I can write this Vm Im sine omega t. This is cos of omega t again. So if I use this identity, you know this, so sine 2a. See, the whole purpose is to reduce in one trigonometric function so that we can analyze. So I can write here, if I multiply and divide by 2 this equation, this 2 will go into the identity part and this 2 will be left in the denominator. So I can write Vm Im by 2, this whole part in identity. So from this identity you can write sine of 2 omega t. So this power expression is instantaneous power, obviously. So this is instantaneous power. You can write this as well. Similarly, you can write somewhere in that part also, inductive part, that instantaneous power expression. You can see the frequency is doubled with respect to current and current or voltage. In the case of current, angle was only omega t, but here the expression for sinusoidal is 2 omega t. So the power curve, the frequency of power curve, when you draw, you will be seeing it is, in one cycle of current or voltage there will be 2 cycles of power. So this is the power expression. Obviously now if I talk about average power here, I will be finding the average value. This is all going to be constant. again you need to find average value of this. And similar to the previous class, again we have solved that by integration also. You know that the average value of a full cyclic trigonometric function over a period is 0. So ultimately you will be getting as the average power is 0. So this is important again. So you see that in both inductive and in both inductive L and C, that is inductive and capacitive loads, the average power is 0. On an average, if you talk, there is no power consumed in this circuit, is 0. Okay, this is also a point. Now, if I draw the power curve, let us plot all the curves together. You know the expression for power from here. It is double times the frequency of the current and voltage. We know all the expression for current, voltage. So we can draw the waveforms and study how this charging, discharging, and how this practically the power game is being played between these things. So let us draw the graphs or the waveforms first. So if I take this as a vertical axis, this is your omega t axis. Anyway, if I take the voltage like this, okay, this white curve is nothing but voltage curve. Similarly, on red, if I say, let us mark the important benchmark omega t points. So these are that every quarter cycle we are going to mark these points because these will be helpful in analyzing this waveform. And we see in this way, obviously maximum value at pi by 2, this is pi, this is again 3 pi by 2, and this is 2 pi. So this is a voltage cycle. As we saw that the current is nothing but leading. So it is 1 quarter cycle lead with respect to voltage. So anyway, I need to see the graph. If it starts from here, it will be beginning early. Before that, before 90 degrees, the curve, voltage of curve can begin to maximum somewhere here. So it will be like this. And like this. Okay. This is what the curve for the current will be looking like. Now let us see the power. So power is nothing but voltage into current, voltage curve into current curve. These graphs will be plotted. So you can easily plot when both are positive. Obviously, current is positive, voltage positive, power is going to be positive. Both are, when one is negative, obviously the power is going to be negative. And this sinusoidal, we have seen that expression. From this expression, you can draw the graph also. See this. And this 2 omega t significance you will be seeing here. So again, when both are negative, again this is negative multiplication will give you positive and the power will be positive. Again one negative, one positive, this will be negative. So this is green curve is your power waveform. So you can easily see if this in this one complete cycle, there are 2 cycles of power. This is the cycle number 1. This is cycle number 2. And we have only seen 1 second of voltage. That was the significance of 2 omega t. Now let us analyze this circuit in terms of charging and discharging, because that has been mentioned in your textbook and it is better to go that way. Suppose this is a sinusoidal supply. This is going to be your capacitance, and we will see the direction of current and analyze the points. Okay. So let us mark the points here. First of all, the points we will be seeing for reference. So this point, let us say it is 1, this is 2, this is 3, this is 4. Okay. And this point is 5. So we will be talking in 1 to 2, 2 to 3 range, 3 to 4 range, and ultimately 4 to 5 range. These sections we will be seeing 4 sections. So here let us talk about power first. It is positive, and you know that power if positive means it is absorbed power. Now let us see the waveform analysis. Now you know that the slope of voltage will be kind of giving you the current expression. If voltage is taken as the analysis waveform, I can see I expression, you know that it is C dV by dt. So this is the expression for current. So now the slope of the voltage will tell you about the current status at different intervals. Now let us suppose see slope of voltage from 0 to from 1 to 2 first. In 1 to 2 region, the slope of voltage is positive, and the current direction, if I say it is in this direction, that is it is positive. So let us say the current is flowing like this in 1 to 2 time. From 1 to 2 interval, if I say, specifically I am drawing this circuit now for 1 to 2. So if a current direction is like this and the slope of this voltage is increasing, dv by dt is on the increasing side. So it appears that the charge is getting accumulated on this capacitor. So by this polarity, as the current is in that direction, so I will say that the charge is getting accumulated on the capacitor as the voltage slope is positive. So I will say capacitor is in the charging state here. Okay, let us talk about 2 to 3. Now obviously voltage is positive, but the current has become negative now. So power is negative. In this case, it is a delivered power. How a delivered power? Now let us see here. From after this point in 2 to 3 region, the slope of voltage is now decreasing. See, the dV by dt is falling down now. Okay, and the current has reversed. Current has reversed. So first of all, you can see mark this as the reverse direction. Now the current is flowing like this. Okay, and you can see that the slope of voltage is now in the decreasing side. The slope of voltage is decreasing. That means current reverse and the slope is decreasing. The charge accumulated in the previous cycle will be getting depleted in this capacitor. So I will say the capacitor is discharging now. And while discharging, these charges are it's depleting from this capacitor. And the charges are depleted, the capacitor is delivering power to the source. So this is the significance. See, voltage slope you need to check. The voltage slope is getting negative. It is decreasing. The rate of change of voltage is decreasing. That means the current also has reversed, and ultimately the charges which were being accumulated now are getting depleted, and this capacitor is discharging. Now let us see the 3 to 4 region. Similarly, now the voltage is still in this direction, the slope, but it is now negative. So what is happening? The current, first of all, again, as you can see, the current is now turning it back. Okay, the current is turning back now again. It is, first of all, it was strengthening in negative direction. Now it is decreasing in negative direction. It is moving towards the zero side. So again, I will say that the nature of current like this, as the voltage slope is now, what is happening? It is again discharge. It is again charging. How? In the opposite direction. What is happening? It is now getting charged in the opposite direction. Now the voltage slope is getting negative, but it is negatively increasing in the opposite direction. So the charges accumulated will be in like this, always like this. Now this is getting negatively charged and this plate is getting positively charged. It is charging in the opposite direction now. Obviously the power is positive, both negative voltage and current. So power is positive, it means it is getting absorbed. And status of C, you can see again it is charging now, but the slope is increasing in the reversive direction. From 1 to 2 it was increasing in the positive direction, now it is decreasing, it is increasing in the negative direction. So the capacitance, you can see it is charging, but now in the opposite direction. That's why the polarity is now getting reversed in this cycle. Now let us talk about 4 to 5. Again you can see the slope of voltage here has reversed. It is now moving towards 0, or now it is decreasing in the negative direction. It is still negative voltage, but the slope is now decreasing in the negative direction and moving towards the positive. So again the voltage behavior has reversed and the current has also again reversed. So what will happen? This current is getting reversed now again. So the previously accumulated charges are now getting again back to the supply. So power is negative, obviously in this case delivered, like you can see from the curve also, but the C is now discharging. This previously accumulated polarity is now, current is reversed, so the charges will be depleting again to the supply. So again we will say discharge. So this is, in this way you can understand how with the slope of this voltage you can understand how this thing is happening. So this is the concept that the charges, flow of charges can be analyzed, that in this case that's how the discharging is taking place, and again the charging is taking place but in the opposite direction. So the polarity of the capacitor is charges on the capacitor in one cycle also are played around between the source and the capacitor. So this is a waveform analysis for this, and you can see from the power waveform the area under power curve is 0, so load average power is going to be 0. So we saw that the real power consumption, the real power consumption, that is real power is also a concept, however, but we see real and apparent power are there is a concept also, but we say for now you understand that real power is absorbed, or better you write for now, let us eliminate this for now. As of now, power is absorbed in resistive circuit only, and to be specific you need to write average power is absorbed in resistive circuits only, and L and C, you can see the average power is 0 when we talk L and C. So all the analysis you have done. So we can also have a comparative study. You can table, you can write the analysis also. If this is R, I say, let us write in this manner also quickly. If purely resistive circuit, by this I mean purely inductive circuit, purely capacitive circuit. In all the cases, okay, the voltage supply I am taking it as V is equal to Vm sine omega t. That has been our standard in all these three cases. And with that, we saw the response of current here was Im sine omega t. Here Im was equal to V by R, which is R is the resistance of the circuit. Here I was Im sine omega t minus pi by 2, and whereas Im was Vm by XL, where XL was the inductive reactance. And similarly, we saw the expression for current here as Im sine of omega t plus pi by 2. Current was leading in this case, where Im was V by, this is actually Vm. This is the maximum value of voltage upon. So Vm by Xc, where XL was omega L, here Xc was 1 by omega C. So the average power here was not 0, it was getting, or you can write this as Vrms square by R also. Here average power is 0, here average power is 0, and you should, if it is better if you know these graphs, it is more easy. So the power graph we were seeing like this in case of the resistor. So average power is not 0 here, here is some average power, but here it was sinusoidal. For this one also, same curve, okay. So if this was omega t, so the frequency was doubled, this kind of so area of this curve, area under curve will be 0, but it will not be 0 here. And the phasor also you can write for short comparison. The phasor, if I say in purely inductive, purely resistive circuit, we saw V was this. In all the circuit, let us assume V as the reference phasor. Then if I say current in this case was in phase with voltage, in this case current was lagging 90 degree, and in this case it was leading 90 degree. So this is a comparative study you can do. And so this is a concept of RLC, and now we have a circuit, a series circuit, which is a series RLC circuit. So series RLC circuit, we can do this analysis of series RLC in two ways. One is the method of phasor diagram, and another we can do the analytical solution. However, the analytical solution is quite a bit tedious. Anyway, we need to understand the results, and for the derivation of RLC circuit, you can use the phasor diagram method. Ask for expression of current. We will be deriving the current expression here also, and several other things will also be in this study. So this is a more complex circuit. So let us see this circuit in the next class. As of now, you can solve the examples in the textbook given, and you can solve some of the problems in the backside related to this discussion up till now. However, there can be good examples are given related to each example. Two examples, I suppose, are given under this L and C circuit. So solve those. Let us see this series RLC circuit in the next class. Thank you.